Hello, and a very warm welcome to everyone who's joined us today. My name is John Norman, and I'm the moderator for today's webinar, in which we will be continuing the conversation from our previous webinar called Predicting Pharmacokinetic Parameters and Curves, where we explored a proof of concept example of how deep learning imputation can help us to accurately predict PK, even when there is little experimental data. Should you wish to revisit the webinar from November 2020, you can find a recording on the Optibrium website. In today's webinar, Matthew Siegel, the CEO at Optibrium, will present Predicting Pharmacokinetic from Limited ADME Data with Deep Learning, a real-world case study where we applied deep learning to guide a project in which potential compounds were displaying good activity profiles, but the team wanted to improve their PK profile to achieve better efficacy. So let's get things underway, and I'd like to introduce the presenter of today's webinar, Matt Siegel. So Matt, in our previous webinar, we described a proof of concept study in the application of deep learning imputation to PK data. Maybe you could outline for us what makes today's case study stand out and possibly the results it has delivered so far.
Thanks very much, John, and thank you for your very kind introduction. Yeah, we're very excited to share the results of this case study with all of you today. As John mentioned, we previously presented a proof of concept study in collaboration with AstraZeneca. And during my presentation, I'll just give you a quick snapshot or reminder of the results of that. But it's great to look at the proof of concept and sort of retrospective analysis. But what's particularly exciting is when you can start to apply these technologies to ongoing drug discovery projects. And without stealing my own thunder, returning some really great results for that project team and helping them to achieve their objectives. So yeah, hopefully you'll all enjoy what we have to share today.
Yeah, thanks, Matt. And before we get things started, I know you want to mention just a couple of our colleagues who have had key roles in this particular project.
Yeah, absolutely. I have the pleasure of presenting this to the audience today and taking all the glory, but actually I do very little of the hard work. And I particularly wanted to mention Bailey Montefiore and Samar Mahmood, both of whom worked on this project and did all the really hard work in terms of building and validating the models and then working with our collaborators to apply them to their project. So it's only appropriate that I mention them and of course our collaborators at Intelligens as well. So thanks for giving me that opportunity.
Yes, absolutely, Matt. And I'm aware of how much we appreciate the immense effort and contributions that the whole team has made in the development of this groundbreaking technology. And with that, let me hand things over to you for this case study presentation.
Great, thanks again, John. It's great to see again so many of you in the audience today. What I'm going to be doing is taking you through this example. I'm just going to start with a few words of introduction, particularly just focusing our minds on some of the challenges with which we're all familiar in terms of working with drug discovery data. I'm going to give an introduction to the underlying method called deep learning imputation that we use in this example, and talk a little bit about the motivation behind applying that to the prediction of pharmacokinetics. Then I'll get on to the meat of the matter, and I will talk about just a refresher of that previous example where we looked at the prediction of rat PK based on sparse in vitro data and in silico predictions. But then really talk about this application that I just mentioned in terms of optimization of pharmacokinetics in an anti-infective project. Draw a few conclusions and then have plenty of time at the end to answer any questions that you may have. Okay, so I guess most of the people in the audience are very familiar with working with drug discovery data and some of the challenges that I've outlined here on this slide. First of all, we know it's impossible to measure all of the compounds of interest in all of the experiments of interest. Particularly in pharmacokinetics, where we have to do in vivo studies, we're very limited in the number of compounds that we can measure in those studies. And so, how do I actually make the most of the data that I have in practice to make better decisions and choose the best compounds? Also, We know that there's a lot of variability in the experiments that we do. Again, particularly in the case of PK, where we're working in vivo, there's an enormous amount of variability in those experiments. We also know that we end up with artifacts and errors in our experimental data. And how do we avoid being led astray by those? False negatives can lead us to miss valuable opportunities, while false positives can lead us to waste time and effort pursuing a hypothesis that later turns out to be based on faulty information. And then, given that we can't run every experiment we might like to, which are the most valuable experiments? What data, if I generate it, will actually give me the most information on which to make decisions? And then finally, again, given the limitations in the experimental data we already have, how can we actually use that to make better predictions for new compound designs and choose the best ones to go forward for synthesis and testing? And these are some of the challenges we'll see how we address in the course of this presentation. So now, as I mentioned, a bit of an introduction to this sort of underlying method that we're going to apply here called deep learning imputation. And where I wanted to start was just with a contrast with the predictive models that we're very familiar with, typically things like quantitative structure activity relationship models, or QSAR. And so predictive models like QSAR models use input features. So in our particular case, we typically use some sort of descriptor for our compounds. And so here we have all the descriptors we can calculate for all of the compounds in our data set. So each of the little orange squares represent a calculated value. We can calculate every value in this matrix. We can fill this in and use our favorite modeling method, whatever that might be. Here I'm showing a sort of illustration of a random forest, but it could be a deep neural network or an SVM or Gaussian process or whatever we want to use. And then we can make predictions for one or more different experimental endpoints. But imputation is quite different. Imputation starts with that limited experimental data that we have. So here we have a matrix of our experiments with our compounds, and the green squares here represent the measurements that have actually been made. And of course, as I just described, most of that data is actually missing and shown by sort of white space here in this matrix. And what imputation does is it uses this sparse data directly as input to fill in the blanks. Again, the purple squares here on the right-hand side, in between those measurements that have actually been made. So this is the idea of imputation. And the particular method that we use is called Alchemite. This is developed in partnership with Intelligens, our collaborators. And what Alchemite can do is it can still take those structural descriptors as input. And what that means is it can learn about that structure-activity relationship between the compounds and the different experiments that we're doing. But by taking this sparse data directly as input, it can also learn about the relationships between those different experimental endpoints. So even though most of that data is missing, where it is present, it contains a huge amount of additional information about those relationships. And that enables us to make much better use of the sparse and noisy data that we have than conventional QSAR models. And again, we can use that to fill in the blanks, again, the purple squares here on the right-hand side, with more accurate predictions than conventional QSAR models. What we've also demonstrated is we can train models that expect only descriptors as input. Where we have no experimental data, typically we describe these as virtual compounds, compounds that have not yet been made or tested, then we can still train a model and make high quality predictions across a broad range of different experimental endpoints that we're interested in. Now, another very important feature is the ability for Alchemite to estimate the uncertainty in each individual prediction. So the model doesn't predict just a single value for every prediction. It actually generates a probability distribution over possible values. So shown here by these little purple probability distributions. And what that means is we can estimate the uncertainty in each individual prediction. Sometimes we see a very broad probability distribution like the one here on the right, and that's the model saying, you know, the value's somewhere around here, but I'm not really sure. I've got a big error bar on that prediction. Whereas in other cases, we can see very sharply peaked probability distribution. That means the model's saying, I'm really confident in that value. It's got a small error bar. And what we've demonstrated in many publications and many presentations is a very strong correlation between the model's estimate of its uncertainty and the observed accuracy on independent test sets. And what that means is we can really highlight the most accurate predictions on which we can base our decisions. This enables us to confidently target high-quality compounds, but also where the uncertainty is greatest, like here on the right-hand side, that of course is where experimental data will add the greatest value. So it helps us to prioritize our experimental resources to measure the most valuable data. I've just given a high-level overview here, but if you do want more information, there's all the details about the method in the publications here at the bottom of the slides. So how does this apply to PK prediction? And so really some of the challenges that we have in PK prediction is first of all, again, as you know, in vivo pharmacokinetics experiments are very time-consuming and expensive. We want to minimize our use of these, not just for cost, but to minimize the use of animal studies. And so we really only want to progress the best compounds to confirm that they have appropriate PK profiles. And unfortunately, we know that conventional QSAR models of in vivo PK properties are notoriously poor. That's understandable because PK in vivo properties in general are often influenced by many different factors, and trying to build a QSAR model that relates the structure of compounds to all of those different factors simultaneously is enormously challenging. And even the in vitro data that we know have complex and often non-linear relationships with pharmacokinetics. So that in vitro in vivo correlation itself can be quite challenging. So can we more accurately predict PK for the compounds based on sparse in vitro data where we have that measured in vitro data? And so to extend the analogy that I just used to describe deep learning imputation, what you can see here is we can think of a scenario where we again have our descriptors, so we can capture structure activity relationships. We also have sparse in vitro ADME data and the results from some PK experiments for some of those compounds as well. And as I described, by taking this sparse data directly as input, it can learn those relationships between these sparse in vitro ADME data and the in vivo PK parameters. Again, we can then fill in the blanks here where we have missing values of those PK parameters. But equally, we have the scenario where we have new compounds that have not yet been measured in vivo, where we only have that sparse in vitro ADME data, and we can use that again as input to predict the in vivo PK parameters. And this enables it to make predictions of PK with the state-of-the-art accuracy, and then help us to make better decisions about the selection of compounds for progression for further study. So it's all very well me saying that, but let's look at some real examples. And first of all, I just wanted to go back to that previous case study that we spoke about and have now published based on prediction of rat PK based on sparse in vitro data and in silico predictions. And this was a collaboration with AstraZeneca. If you want to know much more detail, we were very pleased to present a webinar in collaboration with Nigel Green from AstraZeneca, and there's a link there on the slide, or indeed the results were published in detail in Molecular Pharmaceutics just last year. But in a nutshell, we were very fortunate in that AstraZeneca shared an outstanding data set comprising rat PK studies, both IV and oral, for approximately 3,000 compounds, including 2 replicates for the majority of compounds. So really gold standard data here. These were dose-dependent time concentration curves with many points. From those curves, 9 PK parameters were calculated: oral bioavailability, IV clearance, Cmax both IV and oral, T-half both IV and oral, volume of distribution, area under the curve for both IV and oral administration as well. With that data set, we also had 9 measured in vitro ADME properties, which we could use as input. Again, this data was sparse, but it covered a broad range of properties. These are the common properties that AstraZeneca measure for their compounds. Of course, lipophilicity, but also microsomal clearance in human liver, rat hepatocyte clearance, rat plasma protein binding, human plasma protein binding, solubility, fraction unbound in rat hepatocytes, and CACO2 permeability and efflux ratio. Also, in the case of AstraZeneca, they're very fortunate to have very, very large data sets. And so they also had corresponding in silico models for each of those properties based on a much, much larger data sets than those used in this PK study. So we could also use that information as well. And so here's, again, a quick summary of the results here. This is the R squared, the coefficient of determination for each of those different parameters. And what you can see is really, state-of-the-art quality of prediction for these parameters with, in many cases, coefficient of determination above 0.5. These are very challenging properties to predict, and these are really, outstanding results. I guess one thing that is particularly interesting, and this has consistently been seen in other studies as well, is oral half-life is very, very challenging to predict. But many of these other properties, particularly in IV, are really very well predicted. And just as a comparator, on the right-hand side here, comparing the results generated with Alchemite with those actually published by a group back in 2019. And what you can see is, these are methods using deep neural networks and in combination with physiologically based pharmacokinetics simulations. And here we're able to get, really substantially higher accuracy of prediction. Now, I need to be completely transparent here in that, of course, the data used in this publication is different from this data set, so it's not directly comparable, but it gives you a feeling for what the state of the art is in PK prediction. And also just to mention, and again, all of the details are in the paper at the bottom of this slide, but working with AstraZeneca, they of course applied many other methods based on their internal studies. And I guess what's clear here is that these sort of imputation methods in general are achieving quite similar results to one another. In some cases, one is slightly better than the other, but all within the sort of statistical noise, this sort of imputation approach is working consistently well to make predictions for these PK parameters. So it's all very well to do these proof of concept and retrospective studies, which are really great. But really what we want to do is to start to apply these methods prospectively in drug discovery projects. And we were very pleased to be able to collaborate with a project working on an important and challenging anti-infective objective. Now, unfortunately, I am not at liberty to disclose the name of our collaborator for this project, nor any chemical structures, of course, but they very kindly allowed us to share the results. And basically, the starting point was that our collaborator had achieved a really very good activity profile across multiple different activity experimental endpoints for their anti-infective objective. But they were not yet achieving the PK profile that they required in the mouse model in which these compounds were being studied. And so their goals were to achieve a certain set of parameters in terms of activity and ADME. So they had 5 different activity endpoints here measured in different cell-based assays. They also wanted to get good microsomal stability, good permeability, good solubility, and good plasma protein binding. And this is a scoring profile set up to define the ideal criteria for each of those parameters and the importance of those in terms of the overall trade-off they were willing to make across those parameters. For those of you familiar with our StarDrop software, you'll recognize this as a probabilistic scoring profile. And on the right-hand side are the objectives in terms of the mouse PK profile that they were looking to achieve. So a high Cmax, a long half-life, a low IV clearance, and good oral bioavailability, better than they had achieved so far for their best compound in the series. Now, what data do we have to work with? Well, for this project, they shared a data set containing about 2,260 compounds with 65 different experimental endpoints, including activities, ADME properties, and PK endpoints as well. So the activities were measured in cell-based assays. The ADME endpoints included liver microsome stability, CACO2 permeability, solubility, inhibition of 3A4, and so on, as well as PK parameters measured in mouse models. Now, the activity data was focused on this specific project. This is what they were looking to optimize, but the data set also contained ADME and PK data across several legacy projects. What this means is we can use the model to learn relationships between ADME and PK parameters across diverse chemistry. Now, overall, the data sparsity was about 90%. What does that mean? It means that only 10% of the possible measurements had been made in practice. And in particular, the mouse PK data was available only for about 100 compounds. So in contrast with that previous example, where we had 3,000 data points for PK, here we have a much smaller set of data. And the ADME data was available on between 250 and 1,600 compounds per endpoint, depending on how frequently those different assays were run. So with that data set, we built two types of models. The first was an imputation model. So as I described, this accepts that sparse experimental data as input in addition to the compound structure, and then uses that to fill in the gaps for existing compounds. We also built the virtual model. Again, I described that this model accepts only the compound structure as input, so it can make predictions for compounds that have not yet been synthesized or tested. So let's look at the results. So these are the results on the independent test set. And what we've done is group them here on the left-hand side to show the different activity endpoints. In the middle, we have the in vitro ADME endpoints. On the right-hand side, the mouse PK endpoints. And I guess there's a few things that we can observe here. First of all, the virtual model, that's actually shown in blue here, typically performs less well than the imputation model. That's the green bars in each case. Well, that's to be expected because, of course, the imputation model has access to more information. It has that sparse data that it can use as input to use those relationships between the different experimental endpoints. So we do expect it typically to have better performance, particularly when there are strong correlations between different endpoints, as there are indeed in these activity endpoints, where you can see that the gain is the largest. Also, what you can see as you move from left to right here, that the activity endpoints, typically the model performs better on than the in vitro ADME endpoints, and on the right-hand side, the mouse PK endpoints. Again, we can understand why that is because as you move from left to right, essentially we're looking at more complex properties that are much more difficult to model because they have many different contributions, different factors that influence those different endpoints. And just to point out that particularly for some of these ADME and PK endpoints, there's actually very limited data available, and so hence we expect that model to perform less well than the activity endpoints where there's much richer data available. So that all looks good, but I guess when we start to look at some of the PK endpoints here on the right-hand side, I mean, the R-squareds are not really what we'd typically be looking for to use a model in the context of an ongoing project. So, the best R-squareds here are about 0.4, and in some cases significantly less. So, very often we would look at a model like that and say, well, we can't really use it, so it's not good enough. But this is where that extra capability of Alchemite really comes into its own, because we can use the model's estimate of its uncertainty to focus on the most confident results, the ones that we can rely on to prioritize our compounds. So I'm just illustrating that here for one particular endpoint. So this is the IV clearance in the mouse imputation, IV clearance in mouse from the imputation model. So the overall R-squared is 0.25. So again, really not quite what we're looking for. But on the left-hand side, what you can see is a graph where we have on the x-axis the most confidently predicted percentage of the test set. So here on the right-hand side, we look at 100% of the test set. And you can see on the y-axis, we're plotting the root mean square error, so the average error in that prediction. So for 100% of the test set, the RMSE is just over 0.5 log units. And here on the right-hand side, I'm showing that scatter plot of all the points in the independent test set. And again, the correlation's not great with an R-squared of 0.25. But as we move from right to left down the x-axis here, we're going to focus on the subset of the predictions in the test set with the greatest confidence, the smallest error bar. And what we can see here from this blue line is that as we do that, the accuracy of the predictions increase, i.e. the root mean square error decreases. What this means is as we focus on the more confident predictions, they get more accurate. And we can sort of illustrate that. Instead of looking at 100%, I'm going to look at 50%, the most confident 50%. And what you can see is that these now are much, much closer to this orange line, which is the line of perfect prediction. So let me just go back. That's 100% of the test set. If we focus on the 50% most confident, then you can see they focus in on that line. They are more accurate. If I scroll again to the left, you can see, look at the 10% most confident predicted, and you can see now almost all of them lie pretty much exactly on that identity line. And in fact, we can very clearly distinguish between the low clearance and the high clearance compounds where the model has the greatest confidence. So this enables us to focus on the most confident predictions with which to select compounds. So any method that we use for prioritization needs to use not only the predicted values, but that uncertainty so that we can choose the compounds that we have the greatest confidence will actually succeed. And fortunately, those of you who are familiar with our StarDrop software will remember this probabilistic scoring approach to multi-parameter optimization enables us to combine data from multiple endpoints, assess it against our criteria for success, and explicitly take that uncertainty into account. So what we did, working with the project team, was to define this profile of activities and ADME properties that define the ideal outcome. The virtual model and the scoring profile were then applied to approximately 3,000 newly designed compounds. So these were compounds that had not yet been synthesized and tested, but they had considered would be interesting in expanding around their chemical series. And so with this approach, the compounds predicted to have the highest chance of success, the highest probability of achieving this ideal outcome, were selected for synthesis and testing. Again, taking that uncertainty into account. And here you can see the top ranked compounds. And what you can also see are the the lead compound for the project and 3 additional compounds which were then selected from this list by the chemists in the project. So they were prioritized by this overall MPO score, and then also the actual predictions for these PK parameters were also considered in the selection of those compounds as well. So what happened? So now I've got a table with lots and lots of numbers for you to look at. I'm not expecting you to read them all, don't worry, but just to explain what you're seeing here, this is the previous lead compound here, and then we've got the other 3 compounds that were selected from that list of virtual compounds. For each of them, we have a broad range of data, so the biological activity in these cell-based assays, in vitro ADME profile, and the in vivo PK profile here. The black numbers are the actual experimental values once these compounds were synthesized and tested. The orange values are the predictions from that virtual model. Again, I don't expect you to read them all, but what is particularly nice is that the predictions are reasonably accurate, i.e. almost all of the predictions lie within their error bars from the observed experimental values. So they were getting the trends correct and getting the absolute values within those error bars. But to make it a little bit easier to look at here, let's focus in and give it some color. So here you can see I've colored these by the green representing that it meets those objectives with a good degree. The orange are close to those objectives. The red means that it didn't meet the objectives as defined in that profile. What's interesting is the compounds are not ideal in terms of their in vitro ADME profile. You can see a few yellow and red squares here. But if we focus in on the PK, what you can see is all of these compounds comfortably meet the requirements for that project. So all of the compounds have significantly lower intrinsic clearance in mouse. Clearance in mouse, excuse me, the typo. All of them have significantly higher Cmax. All of them have much higher exposure, oral exposure, and higher oral bioavailability. Again, that illustrates the challenge of that in vitro in vivo correlation. Sometimes you get some surprises. So it was very nice to see that the model picked up on the fact that even though these weren't optimal from the ADME in vitro perspective, they were predicted with good confidence to meet those PK parameters. So in summary, what we did is we built these deep learning imputation models using a data set comprising both the project-specific activities, ADME, and PK data across multiple projects. They were applied to this virtual set of compounds proposed by the chemist for synthesis and testing. And from that, 3 high-priority compounds were selected, synthesized, and tested. And by focusing on the most confident predictions, we were able to focus on those compounds with the highest chance of success, even for these very challenging properties to predict. And all of the selected compounds, all 3 of them showed good activity profiles and demonstrated that improved PK profile that was required by the project, thereby achieving the objectives for that project. So just to wrap up with a few conclusions, it's great to have a nice algorithm, these fancy AI algorithms, but actually applying them in practice is often challenging. And it's really important to put these methods directly in the hands of the decision makers working on these projects. So what we have developed is a platform called Cerella. And what this does is it really enables a sort of active learning in drug discovery to guide these projects in a much more natural way. So first of all, it connects directly with the data sources for our users, for their projects. And it automatically does that very time-consuming, very boring, but very important update and preparation of experimental data for model building. So applying the sort of transformations and cleaning rules to get the best model performance. It populates that sparse matrix we've been talking about of compounds and experiments. Again, the little green squares are the measurements that have been made, and the white squares are those that are missing, have not yet been made. It then applies this Alchemite deep learning imputation model to that sparse and noisy experimental data in the ways that I just described, and it automatically builds and, of course, updates those models as new data become available, so that you're always working with results based on the latest information. Of course, as we've discussed, it can fill in the blanks in that matrix. Now, that brings us a new challenge in that we might have in a large pharma company, maybe millions of compounds down this axis, and maybe thousands or even tens of thousands of different experimental endpoints along the top axis there. In practice, less than 1% of that data will actually have been measured. But one can imagine if we fill in the other 99%, suddenly we have a true big data problem there. This is what we describe as the massive matrix, which can contain tens of billions of data points. And so Cerella also scales to manage that very large set of data to make it very easy to search and find those valuable conclusions and interesting results to take those projects forward. And of course, those need to be made available in a seamless and user-friendly way. So we, of course, use our StarDrop software as a front end where our users and we work with that data, but accepting that you may have your own ways to visualize, analyze, and work with data and use these models in the ways that I've just described. The same information in same models, the same results are available from any platform that you wish for those of you techies in the audience, via a RESTful API. So in conclusion, predicting in vivo endpoints such as PK is very challenging. Complex multi-mechanistic factors can influence that outcome, and the experimental data are very variable. And I hope I've demonstrated how this deep learning imputation approach can offer a new way to leverage that data and more accurately predict PK. It's also important that we take into account not only the predicted values, but the uncertainties to enable us to confidently target high quality compounds, or on the other hand, to confidently reject poor compounds as well. That you can save a lot of time and effort where you know that there's a very low chance of that compound meeting your objectives. So if you want more information, my email address is there, matt@optibrium.com. I mentioned the publication in collaboration with AstraZeneca. So here you can see the reference again, and of course our website at optibrium.com. And finally, just a few words of acknowledgement. Again, to come back to the sort of introduction, I get to talk about all of these great results, but the result of lots of people's hard work, including, I mentioned Samar and Bailey, but also our former colleague Ben, our collaborators Gareth and Tom at Intelligens, and of course, in terms of that paper that we published and the previous case study, many people at AstraZeneca, and all of the project team members at our unnamed collaborator. So that's the end of the presentation. I can see we already have some great questions coming in. Right, we have one question about the statistics, and particularly around the R-squared values that I was quoting, and different types of R-squared values. And you're right that there is often a lot of confusion around this. There are two R-squareds that are often quoted. One, the one that we're using, which is the coefficient of determination, and the other, which is commonly quoted, which is the squared correlation coefficient. In all of our work, we quote the coefficient of determination. This is a measure of the quality of the predictions relative to that identity line, the line of perfect prediction, where the predictions would be exactly equal to the observed value. So an R-squared of 1 means every single prediction is exactly equal to the observed value, which of course is impossible because there's noise in the experimental data. An coefficient of determination of 0 is equivalent to a random numbers, essentially. And you can actually get R-squared values less than 0, which means worse than random. In fact, it can go down to minus infinity. And that is where the error in your prediction, it becomes greater than the total spread of the available data. So this is a very rigorous way to assess the quality of predictions. We prefer that over the squared correlation coefficient because the squared correlation coefficient is a measure of its fit to the best fit line between the observed and predicted. Now that best fit line may not be the identity line of perfect prediction. So the coefficient of determination is guaranteed to be equal than or less than the squared correlation coefficient. And so it's a more rigorous way to calculate it. And so that's the one that we always quote. And apologies if there are any confusions from that. Okay, let's see. How did you validate uncertain predictions for properties with no true uncertainty available? I think I showed you an example of that plot there. So what we did is we looked at the, in fact, let me go back to that slide. This slide here, where we actually look at that correlation between the confidence in the prediction, the size of the uncertainty, the error bar around that prediction, with the observed accuracy. So here what you can see is as you go from right to left, we're focusing on the subset with the greatest confidence, and the accuracy also increases. Just to give you a feeling of absolute scale, the blue line here represents the root mean square error in that prediction. The dotted line here actually represents Alchemite's estimate of the uncertainty. So you can see in this case that it's also getting in absolute terms the size of those error bars correct. A related question is when I sort of illustrated those probability distributions when talking about the method, go back to that slide here, an observation that we assume it's Gaussian. Do we assume it's Gaussian? The answer is no, actually. These are just illustrations generated just to show the principle. We are not fitting a Gaussian or looking at a posterior probability distribution. What we actually are looking at is what we actually generate is an ensemble of predictions from many different models, and that ensemble gives us a distribution that may or may not be Gaussian distribution. In fact, it's often not, but again, just really illustrating this for simplicity. Right, so selection of early molecules for in vitro or in vivo data generation. Typically, a project scheme uses a potency cutoff, then microsomal stability cutoff, then in vivo PK with rapidly decreasing data points from left to right. So the in vivo PK data ends up being sparse and representing only a small subset of compounds meeting the potency and microsomal stability criteria. For imputing, is it better to cast a wider net early on, e.g. try to look at in vivo PK of compounds that span a full range of potency microsomal stability? That's a really great question. And in an ideal world, yes, absolutely, it would be great to do that. Unfortunately, we rarely work in an ideal world, and people are very reluctant to progress compounds that have poor results in early assays. And so we're often in a situation where we don't have the luxury of a broad spread of different values for each of the parameters. That can be a limitation, but as you can see here is, by taking particularly that sort of legacy data into account, we did get a broad enough range of different results both in vitro and in vivo PK studies to identify those correlations and to make these high quality predictions. So in practice, and we've done this in several other projects as well, it seems to work. We have enough data with which to build these models. But yes, if you wanted to learn faster with less data, then ensuring you had a good spread early on would be very good. This is the concept of exploration versus exploitation. You want to exploit the best compounds, but it's also worth investing some time in exploring a diversity, not only of structure, but also of property values. Okay, so would you argue that the confidence estimates mean that an imputation model with R squared of 0.4 is good enough to use in MPO with the probabilistic scoring approach? At a glance, the IV clearance model did not appear to be used in the MPO profile. Did I overlook something? No, you didn't. You're absolutely right that, and that particular MPO profile, which we showed you for that project, we were focusing for that initial prioritization on the in vitro ADME properties and the activity. So that's absolutely right. But then we did also look, once we had whittled it down to a smaller number of compounds, at the PK parameters. And what you can see in the actual ones that were chosen, they also had a good degree of confidence with only about a factor of 2 uncertainty. So we did look at that uncertainty to make sure that we weren't picking a compound that was predicted to be absolutely great, but with a huge error bar. So you're right, in the case of that MPO, we didn't. But actually, the ADME data, the ADME models themselves had a wide range of different uncertainties. And so by focusing on those where the models had the greatest confidence they were going to meet our objectives, that enabled us to rigorously prioritize those compounds. Equally, we can confidently reject compounds where the model has high confidence, low uncertainty in poor values. And in the middle, of course, you will have some that may have greater uncertainty. Sometimes that's your best bet, actually. If you don't have any compounds that you're confident are good, at least picking some that look to have a high probability of being good, albeit with a big error bar, is worth exploring as well. So it says, so StarDrop allows real and virtual compounds to coexist with all predictive models applied. Can all of this be shared throughout the whole organization? Yes, absolutely. So when connected with Cerella particularly, you can actually have the imputed data. So where experimental data is available, it has the actual experimental value. Where not, it will automatically fill in those missing values with the imputed values, and each with an error bar associated with it. You can have that in a StarDrop project. You can use it to prioritize your compounds and data. and you can very quickly be able to share that information by sharing the StarDrop project file as well. So here another really good question. So the example does not focus on optimizing free drug levels. Maybe your collaborator's fault. It looks like you have therefore selected high plasma protein binding compounds to reduce hepatic extraction ratio and oral bioavailability without addressing the free drug issues. Have you shown the ability to predict free drug levels in other work you have done? Yeah, really good question. Again, we didn't set the criteria. You're absolutely right, and it may well be that that the high protein binding will reduce the free drug concentration. We have not explicitly using Cerella optimized free drug concentration, but yes, certainly many of our collaborators have used scoring profiles to also simultaneously look for low protein binding. I would say it's not entirely fair in that in the scoring profile, we were looking for compounds with relatively low or relatively high fraction unbound, I should say. So it was taken into account, but you are correct that that some of these are somewhat higher than we would like, that's for certain. Okay, so just going back to the dashboard, I noticed that you merged the in vitro with the in vivo data to generate the model for prediction. Shouldn't you notify the nature of data to enhance the accuracy of the results? The nature of the data doesn't make a difference for the accuracy of the results. So what we're doing there is using that relationship between the in vitro and the in vivo data to better predict the in vivo. So we don't have to annotate that explicitly because the modeling process will identify those correlations sort of automatically to highlight that, to make those predictions. There is an argument to say that there's a certain direction of imputation. So you don't want to use the in vivo data to impute the in vitro data. So because obviously they will be typically measured later in that screening cascade or in that process. So yeah, you can actually encode that and say you could only use, you can only impute sort of in one particular direction. So that's certainly possible to do. We didn't in that particular case, and where we've tried it, it hasn't actually proven to be so necessary, and that's because the model recognizes the difference in the sparsity of the data. As we discussed earlier on, we have more data for in vitro than in vivo, and so it tends to leverage the correlations in that direction preferentially, even without having to explicitly annotate that. But there are opportunities to further refine the process in that sort of way. There's a few questions here with regarding the size of data sets that are necessary. So there's no simple answer to this. In general, the more data you have, the better. There are some provisos in terms of having an appropriate spread of different values, appropriate variance in that data. But typically, the more you have, the better. What is the absolute minimum? It depends on the strength of the signal within the data. It depends on the complexity of the property you're trying to model and the diversity of the chemistry that you're looking to model as well. So to give you rules of thumb, typically we would feel more comfortable with at least 50 data points for an endpoint, for one experimental endpoint, to be able to model it. Ideally, as we saw in this case, we had about 100 compounds with PK values for the mouse PK, so that was, you know, a good size to start with. The absolute bare minimum that we would use is 20. The simple fact is, if you have a 20% test set from a data set of 20, then you've only got 4 compounds in your test set, so it becomes very difficult to do a rigorous sort of statistical validation of that. So we draw the absolute bare minimum at 20. I would not expect to get a good model from 20 data points, but what you can start to do is get information on the most valuable additional measurements to make to inform that model. So the idea of active learning. And so that enables you to much more quickly bootstrap to a high quality model from that small starting point. Below 20, actually Cerella will completely refuse to build a model at all. Okay, so a follow-on question from one earlier on. So the question is, do you want to focus on the most confident predictions before performing MPO scoring if you have a low R-squared? So you certainly want to take that uncertainty into account. The beauty of the probabilistic scoring approach that I briefly mentioned is that you don't need to do that beforehand. It will take that uncertainty explicitly into account. So it will help to prioritize compounds with the highest probability of achieving the ideal outcomes that you want. So you don't have to sort of pre-filter it based on confidence before you do the scoring. It will take that into account automatically. It will also help you to determine when you can choose between compounds with confidence, when the data you have gives you the resolution to make that decision, or where you might need more data before making that choice. And so if you'd like to know more about the probabilistic scoring approach, there is a reference here on the slide, which I'll just bring up, which was in Current Pharmaceutical Designs some time ago, back in 2012. Right. Well, I appreciate all of you who have stayed on the line so long through the Q&A session. We had lots of great questions. So just a final word of thanks for joining us today. If you want more information, please do contact us at info@optibrium.com. And just a final reminder that a recording of the presentation will be on the Optibrium community site very shortly. You will receive an email with a link to that in case you want to go back and refresh your memory, but equally, please feel free to share that with any of your colleagues who might also find this interesting. And also on our community site, you will find many different publications and other presentations and webinars that you may find interesting in this context and in many other areas as well. So thanks again, and we look forward to seeing you at our next webinar soon.